Okay, greetings. So, welcome to today's class. So, just a quick recap of what we did yesterday. So, in yesterday's class we considered the air standard Otto cycle and the air standard diesel cycle. We looked at the processes of those two cycles and we identified that the main difference between them was that of the heat addition process, right. In the Otto cycle, heat addition was assumed to take place at almost constant volume. In the diesel cycle, heat addition was assumed to take place at almost constant pressure. That is the main difference, and we went and did some analysis using the conservation of energy and used the process relationships for isentropic process and the ideal gas equation of state to get expressions for the thermal efficiency of the two cycles. So, and we just started off with one case where we wanted to compare the Otto cycle and the diesel cycle. So, as we realized from the analysis, if we fix the same value of compression ratio R, the air standard Otto cycle has a higher thermal efficiency than that of the diesel cycle. We just wanted to essentially investigate it further. So, we considered one case where we had the same compression ratio and heat addition. Today I am just going to do one more example and then we will move on to what is called as a dual cycle. Okay. So, let me do a second case where we still consider the same compression ratio for both the Otto and the diesel cycle. But now let us consider the same amount of heat being rejected. Okay. So, that is the scenario that we are going to consider now. So, let me once again quickly draw the TS diagram for the Otto cycle, and then we will look at what happens in terms of the diesel cycle. So, let me call this as 1O, this is 2O, and we have constant volume heat addition. I go to 3O and then isentropic expansion, come to 4O, and then constant volume heat rejection. Okay. So, we need to carefully mark all the processes when we draw these diagrams. Okay. So, this is the TS diagram. Now, as we have already discussed, the area AO, 1O, 4O, BO is equal to the heat rejected in the Otto cycle, and the area AO, 2O, 3O, BO is the heat input given to the Otto cycle, right. Okay. So, that is something which we have already learned. Now, once again let us start from the same initial state. Okay. So, 1D is the same as 1O. Then what we do is that we have isentropic compression. So, where should 2D be? Same as 2O. Why? Because same compression ratio. So, as we realized from the analysis, T2 was T1 times R power gamma minus 1. So, T1 is the same for both cycles, R is the same, that is the condition we are given. So, T2 should be the same. So, 2D should coincide with 2O. So, now let us draw the constant pressure line passing to 2D, and that is going to be something like this, right. So, that is the constant pressure line, right, passing through 2D. So, we are given that the heat rejected is now the same. Okay. So, that means AD, the area AD, of course AD is the same as AO now, okay, AD 1D 4D BD should be equal to AO 10 4O BO. Okay. So, these two should be the same. So, what does that tell us? Because even in the diesel cycle, heat rejection is done at constant volume, right. Okay. So, AO 1O and 1D coincide, AO and AD coincide. So, what can we say about 4D? It should be the same as 4O, right. Otherwise there is no way the area AD 1D 4D BD will be the same as AO 10 40 BO, because in both the Otto cycle and the diesel cycle heat rejection takes place at constant volume, and there is only one constant volume line passing through 10 and 1D. So, the point 4D must coincide with 40. So, then the state BD will be the same as BO, right. So, we have identified 4D. Now, how do I identify 3D? Please remember 3D 4D is isentropic expansion. So, 3D must lie on the vertical line passing through 4D in the TS diagram. So, and then 3D should also lie on the constant pressure line passing through 2D. So, the intersection of the constant pressure line passing through 2D and the constant entropy line passing through 4D should be 3D, and what is that point? It is here, right. So, as a result this is my diesel cycle, correct. So, we have identified this one. So, please note the area AD 2D 3D BD is the heat input given in the diesel cycle. Now, we know that the thermal efficiency is going to be equal to 1 minus Q out by Q in. Okay. We are given that Q out in the Otto cycle and Q out in the diesel cycle are pretty much the same. That is like I reject the same amount of heat energy, okay, in both the cycles. Now, what can I say about Q in? So, please note Q in the Otto cycle is AO 2O 3O BO, right. Q in the diesel cycle is AD 2D 3D BD. Which is bigger? Otto cycle, right. So, then what can I say about the thermal efficiencies? Please note that the expression for thermal efficiency is this. So, in the second term that appears in the thermal efficiency, Q out, which is the numerator, is the same for both cycles. Q in, which is the denominator, is larger for Otto. So, the ratio is smaller for Otto cycle, right. So, we are subtracting a smaller number from 1 in the Otto cycle. So, which efficiency will be greater? Otto, right. So, the Otto cycle will have more thermal efficiency than the diesel cycle as long as the compression ratio is the same, right. So, that is the main takeaway, okay. But as we will discuss when we look at the actual combustion process, the phenomena of knocking typically restricts the maximum compression ratio in petrol engines or gasoline engines, right. So, we are not going to have the same compression ratio in gasoline or spark ignition engines when we compare them with diesel engines, right. So, as a result we will see that the compression ratios would not be the same. However, if the compression ratios were the same, we see that the Otto cycle is more efficient than the diesel cycle. Okay, we will discuss this point as we go along, right. As we go to actual engine performance and do the analysis, we will discuss it further. Okay. Yeah. So, the next air standard cycle that we will discuss is what is called as a dual cycle. So, in the last class when we motivated the Otto cycle and the diesel cycle, the constant volume heat addition process and constant pressure heat addition process are typically motivated by looking at the actual engine curve, right. In reality, like if you look at the actual engine data, we are not going to see the combustion process happening at almost constant volume or almost constant pressure, okay. It is going to be a mix of both. So, the question is, if the Otto cycle and the diesel cycle do not approximate the actual cycle well enough, what is an alternative to do first cut analysis? So, that answer is the dual cycle. So, in the dual cycle what we do is we consider that the heat addition process takes place in two phases, The first one is at constant volume, the second one is at constant pressure. Of course, we are making all these approximations so that we can derive analytical expressions which are simple enough to do a pen and paper analysis. So, that is the motivation. So, in a dual cycle we consider that the heat addition process takes place in two phases. So, if I were to draw the TS diagram for the dual cycle, it will look something like this. So, I will start with state 1. What will happen is that, like, I will go to state 2, the compression process is going to be isentropic. Then there will be two heat addition processes, one at constant volume, another at constant pressure. So, first I will have a constant volume heat addition process, then I will have a constant pressure heat addition process, then we will have isentropic expansion, then the heat rejection process is reasonable enough to be assumed at constant volume once again. Okay. So, this is the dual cycle. So, you can see that the heat addition process now consists of two sub processes, okay, constant volume process and a constant pressure process. So, if I were to draw the PV diagram for the same process, so and then I draw it here. So, 1 to 2 will be isentropic compression, 2 to 3 will be constant volume heat addition, 3 to 4 will be constant pressure heat addition, 4 to 1 is isentropic expansion, sorry 4 to 5, and 5 to 1 will be constant volume heat rejection. So, the processes will take place like this. Okay. So, consequently, there are two heat addition process, let us call it as Q in 1 and Q in 2, and this is the heat rejection process Q, right. So, that is the PV diagram of the dual cycle. So, I hope it is clear why the term dual came into being, right. So, the heat addition process has two stages, one first at constant volume, then at constant pressure. So, the idea is whether the dual cycle can better approximate the actual engine cycle. Okay. So, in this analysis we are using the PV diagram. Just a quick aside, like in engine analysis you will also encounter the P theta diagram. Okay. P theta diagram, theta being the crank angle or the crankshaft angle. Okay. So, as we know, in a 4-stroke engine, one operating cycle is completed in 2 revolutions of the crankshaft. So, this is one cycle. So, how many degrees will constitute one cycle in a P theta diagram? Suppose if we were to plot a P theta diagram, I start from 0 degrees, right, one cycle will go till 720. Okay. So, it will be spread out. So, you will not see a loop like this, okay, because then you need to mark VDC, TDC repeatedly. Okay. Here we mark at one volume and then we understand what is happening. So, there it will be spread out. Okay. So, P theta diagram is also used for some analysis, okay, like in engine, and you can obviously see that there is a 1-to-1 correlation between V and theta. Okay. Once you fix an origin, a starting point, you can always figure out, you can always correlate V and theta, right. So, these diagrams are what are called as indicator diagrams. Okay. The term indicator diagrams is used to represent these diagrams. Okay. Fine. So, that is a quick aside, right. So, now let us come back to our analysis, right, of the dual cycle. So, once again the thermal efficiency of the dual cycle is, as we know from first law of thermodynamics, what we derived is going to be 1 minus Q out by Q in. However, now Q in will consist of two parts, Q in 1 plus Q in 2. Okay, so those will be the two parts. Now, from yesterday's from the last class's analysis, like we know how to write the expressions for Q out, right. So, let me put the magnitude to be consistent. So, we are going to look at the magnitude of Q out. Okay. So, we already know how to do this analysis, right. So, let me directly write the expressions. So, what do you think will be Q out now? It will be U5 minus U1, correct. So, what will be Q in 1? It will be U3 minus U2, because the constant volume heat addition process is from 2 to 3. Then what about 3 to 4? It will be now H4 minus H3, right, because it is a constant pressure heat addition process. Okay. So, considering constant specific heats, we are going to get Cv times T5 minus T1 divided by Cv times T3 minus T2 plus Cp times T4 minus T3. Okay. So, those are that is the simplified expression. Okay. So, here we are considering constant specific heats. All right. So, now the question that arises is the following, right. So, how do we then simplify, right? We have all temperatures. Now, by now we are familiar with the process, right? We have to use the process relationships. Let us go from one process at a time, and then like we eliminate the temperatures, right. So, but before doing that, like quick definitions, there are two parameters, like the first one is what is called as a pressure ratio Rp, which is defined as P3 by P2. So, in the constant volume heat addition process, the volume is constant, but the pressure is increasing, right. So, the pressure ratio R subscript P tells me what is the ratio of P3 and P2, okay, that we encounter in the constant volume heat addition process. And we have already encountered the cutoff ratio, all right. Cutoff ratio R subscript C is going to be now V4 by V3, because that is the 3 to 4 is the constant pressure heat addition process, right. So, that is the cutoff ratio. Now, let us look at each process at a time. So, now if we look at 1 to 2, what is 1 to 2? It is isentropic compression. So, what is the process relationship? We will have T1 V1 power gamma minus 1 will be equal to T2 V2 power gamma minus 1. So, that essentially results in T2 being T1 V1 by V2 to the power gamma minus 1, right. And what is V1 by V2? R. So, this is a standard relationship, by now we are familiar with this, right. So, T2 is going to be T1 times R power gamma minus 1. So, then we consider the constant volume heat addition process 2 to 3. So, we know that since the volume is constant, the ratio of temperature is going to be equal to the ratio of pressures. How do we get that? From the ideal gas equation of state, right. So, this is the process relationship for this constant volume heat addition process. So, this will give me T3 equals T2 times P3 by P2. What is P3 by P2? Rp. And then I substitute for T2, I am going to get T1 R power gamma minus 1 times Rp, right. Okay. So, that is the second process. Then let us look at the constant pressure heat addition process. So, what is going to be the process relationship for constant pressure heat addition process? T4 by T3 is going to be equal to V4 by V3. So, this implies T4 is equal to T3 V4 by V3, and V4 by V3 is RC. Then I substitute for T3, we will get T1 R power gamma minus 1 RP RC, right, that is T4. Then we consider process 4 to 5, which is isentropic expansion, that is going to be T4 V4 power gamma minus 1, that is going to be equal to T5 V5 power gamma minus 1. So, this will give me T5 equals T4 V4 by V5 gamma minus 1, and what is V4 by V5? V4 by V5 I can rewrite it as V4 by V3 times V3 by V5. What is V4 by V3? It is RC. What is V3 by V5? V3 by V5, it is going to be 1 by R. V5 by V3 is R, V3 by V5 is going to be the reciprocal of R, right. So, I will have RC by R. So, this will be RC by R to the power gamma minus 1. If I substitute for T4, what am I going to get? R power gamma minus 1 will cancel off. I will get RP RC to the power gamma. That is what I will get for T5, right. Now, we are all set. So, we go back and then look at the thermal efficiency of the dual cycle. So, that is going to be 1 minus T5 minus T1 divided by T3 minus T2 plus gamma times T4 minus T3. So, what have I done? I have just divided by CV, right, and Cp by Cv is going to be the ratio of specific heats, correct. So, now we go and substitute all the temperatures. So, what will happen? T5 is going to be equal to T1 Rp Rc power gamma minus T1, and in the denominator T3 is going to be T1 R power gamma minus 1 Rp, T2 is T1 R power gamma minus 1, that is the first term, then plus gamma times T4 is T1 R power gamma minus 1 Rp Rc minus T3, right. T3 is what? T1 R power gamma minus 1 Rp. Am I correct? So, I am just substituting the appropriate values of the temperatures that we have already derived. So, if we simplify, we can immediately see that this T1 can be cancelled in the numerator and denominator, right, in the second term. So, what we are going to have is the following. So, you can pull out R power gamma minus 1 common from the denominator, then we are going to have in the numerator Rp Rc power gamma minus 1 divided by Rp minus 1 plus gamma Rp Rc minus 1. Okay. So, this is what we will have. So, this is the expression for the thermal efficiency of the air standard dual cycle. Okay, you can immediately observe that it depends on the compression ratio R, the pressure ratio Rp, the cutoff ratio Rc and gamma, right. So, those are the 4 parameters that affect the thermal efficiency of the dual cycle. Okay. Now, we can immediately observe from this expression that if RC equals 1, what happens to the thermal efficiency expression? If RC is 1, what happens?
Equal to that of Otto cycle.
The above expression reduces to 1 minus 1 by R power gamma minus 1, which is nothing but the Otto, right. If RC is 1, you see that the second term vanishes, this term vanishes, and the denominator becomes Rp minus 1, Rp minus 1, Rp minus 1 cancel. We are going to get 1 minus 1 by R power gamma minus 1. Am I correct? So, that is the thermal efficiency of the air standard Otto cycle. So, if RC is 1, that means that, like what does it mean? There is no constant pressure heat addition, right. The states 3 and 4 coincide, alright. So, that is a meaning. So, if Rp is 1, what do you expect? Of course, now there is no constant volume heat addition process. So, if you substitute Rp equals 1, this is going to become 1 minus 1 divided by R power gamma minus 1 multiplied by Rc power gamma minus 1 divided by gamma times Rc minus 1. And what is this expression? If we go to the analysis of diesel cycle that we did, that is the thermal efficiency of the air standard diesel cycle, correct. So, you can see that the dual cycle boils down to the diesel cycle, okay. And in general, for the same value of R, okay, compression ratio, we already learned that the thermal efficiency of the Otto cycle is going to be greater than the thermal efficiency of the diesel cycle, and the thermal efficiency of the dual cycle is going to be somewhere in between, okay. So, this can be shown, right. So, essentially the value of thermal efficiency of the Otto cycle will be the highest, followed by the dual cycle, followed by the diesel cycle for the same value of compression ratio, okay. So, these are 3, let us say we call 3 observations, okay. So, let me call them as A, B and C, okay. So, some points to note, okay. So, that completes a simple analysis of what are called air standard cycles. We learned the Otto cycle, the diesel cycle and the dual cycle, and the main advantage of these cycles is that, like, despite the assumptions that we make, it can be used to get a first cut idea about the particular engine's performance, right, using some approximations, like so. That is the main idea.